So, welcome back to lectures on engineering mathematics 2, and this is lecture number 27 on polynomial interpolation. This is second lecture on the same topic. So, in this lecture we will be talking about forward and backward difference table, and these difference tables will be used to derive this Newton's forward interpolation formula as well as the Newton's backward interpolation formula. So, just to recall, in the previous lecture what we have done, we have discussed what is the polynomial interpolation. So, it is the method of determining the polynomial that fits a given data set, and we also talked about the existence and uniqueness. So, basically there is only one polynomial which passes through a given data point. So, if there are n plus 1 data points, then there will be only one polynomial of degree less than equal to n that passes through all the points. And we have also derived a formula for obtaining error. So, the error between the function and the polynomial approximation. So, that will be computed by this formula which uses the derivative at n plus. So, n plus 1th derivative of the function. So, having this, now we will be talking about different methods for determining interpolation or interpolating polynomials. So, although there is a unique nth order polynomial that fits given n plus 1 data points, but there are a variety of mathematical formats in which this polynomial can be expressed. So, for instance, which we will be talking about in this lecture, we have the Newton's forward and backward interpolation polynomial, and we have also the Newton's divided difference formula, that is a slight variation from the previous one, and we will be also talking about the Lagrange interpolation formula next lectures. So, coming now to Newton's forward and backward formula, we will take these points x 0, x 1, x 2, x n, and we assume that they are equally spaced. That means, x 1 is x 0 plus h and this x 2 will be x 1 plus h. So, there will be a difference of just h. So, we need to talk about these finite difference operator, because some operator will be used in these formulas. So, therefore, it is important here to use this finite difference operator, because that is easier to define these formulas or to derive these formulas using these shift operators. So, the first shift operator we are talking about this E here. So, E of f x I will be f x I plus h. So, when we operate this E on f x I, so if we are operating this E on a point here on a data point here f x I, then this is nothing but the value of this function at x I plus h. So, at the next data point. So, it will shift the function value here. There is another one, forward difference operator, which uses this symbol here delta. So, delta f x I will be just f x I plus h minus f x I. So, it is a difference operator. This is called the forward difference operator. We are going for in the forward direction, then minus the value of f at the previous point. So, this is called the forward difference operator. There is a backward difference operator as well, which is denoted by this nabla f x I, and here it is other way around, that f x I minus f x I minus h. So, the value at previous data point. So, these are basically the three operators which we will be using here in this lecture. So, the shift operator E, the forward difference operator delta, and another difference operator which is backward difference operator is this nabla. Then also there is a central difference operator. Just for completeness, let me explain this also. Its symbol is delta f x I, and this is again a difference operator, and these two differences are used, f x I plus h by 2. So, it takes the value at x I plus h by 2 and then subtract the value from the x I minus h by 2. So, this is the central difference operator. So, having these operators, mainly the first three operators, shift, forward and the backward, we will continue with some relations between them. So, let us assume for simplicity that f at x I is denoted by f I, f x I plus h is denoted by f I plus 1 and f x I plus h by 2 is denoted by f I plus half, just for simplicity of writing. So, here it can easily be verified now that this delta f I is backward delta f I plus 1 and also this is equal to this delta when operated on f I plus half. One can easily see all these relations, it is not difficult. For instance, here this delta f I will give, as per the definition, I f I plus 1 minus f I. When we are here in the backward, so it will give f I plus 1 minus f I, which is same, and when we are at this central difference operator, so we will give here f I plus the half will be added. So, we have I plus 1 and then again f I. So, all these three are same. So, therefore, we are telling here that the forward operator on f I is equal to backward operator on f I plus 1 and this is equal to central difference operator on f I plus half. So, these three are equal here. Also, we can easily prove again that this forward delta operator is equal to E minus 1, which again one can easily see when we apply this delta on f I, what we will get? We will get f I plus 1 minus 1 minus f I, sorry, and then here also when we apply this f I on E minus 1. So, we have E f I, which is f I plus 1 and then minus f I again. So, again these are same. So, we can say that this delta is nothing but this E minus 1. Similarly, the other relations, the backward delta here, it is 1 minus E minus 1, and similarly we can prove this by just operating two operators on f I and the result will be the same. So, also we have the relation that delta is nothing but the e power half and minus e power minus half. So, again one can see when we operate these two operators on f I and we will receive the same value at the end. So, having these relations, so we can now move further. So, we have the higher order differences also. This is what we have discussed, they are first order differences. We can talk about the higher order differences as well. For example, delta 2 operated on this f x I, that means delta operated on this delta f x I and this delta. So, delta f x I is f I plus 1 minus this f I, and so we have the delta on f I plus 1, that is f I plus 2 minus this f I plus 1, that is when we operate delta on f I plus 1, and when we operate delta on f I, we will get f I plus 1 minus f I. So, forward difference operator, we will go in the forward direction and then subtract the value f I. So, which can be written in this form. So, f I plus 1 minus 2 f I and plus f I. Similarly, we can talk about the second order backward difference operator, which is delta del 2 here f I, and here we have again the two times we operate, and so the first time when we operate is f I minus 1 and we will operate again this backward operator. So, f I minus 1 and here again f I minus 1 minus f I minus 2 and when we combine, so we are getting f I minus 2 f I minus 1 and plus f I minus 2. So, these are the second order difference operators. We can talk about the third order, fourth order or nth order in general, but we do not require at present. So, we will move further just but the idea can be extended of course for the third order and the fourth order. It is very clear now from here. So, the forward difference table, usually when we compute these differences, so we can use naturally the formula which we have derived, but they are a bit difficult to again to remember and then to apply on the given data set. it is much easier to form this forward difference table, and from the table we can easily pick all these values for the first order operators, second order operators, or third order or fourth order operators. So therefore, these tables are very useful. So, given this x, so for instance, this is just an example, x naught, x 1, x 2 and x 3, the 4 data points are given, and the value of the function, so f 0, f 1, f 2 and f 3 is also given, and then we want to compute the forward difference operators, first order, second order and the third order. So, what we do usually, and we can verify with the formula which we have derived, this first order differences here will just come when we subtract f 1 minus f 0. So, from here f 1 minus f 0, from here f 2 minus f 0. So, here f 2 minus f 1 will come, here f 1 minus f 0 will come, and here at third place f 3 minus f 2 will come. So, with just simple differences here we can get the first order difference operator, which can be noted here that this first order difference operator is nothing but we go in the forward direction and subtract the same. So, here the delta f 0 which will appear at this place, delta f 0 which will be nothing but f 1 minus f 0. So, we go with the difference here f 1 minus f 0, then f 2 minus f 0 and then f 3 minus f 2, and we will get these delta f 0, delta f 1 and delta f 2. So, delta f 1 is nothing but f 1 minus f 0, delta f 2 is nothing but the f 2 minus f 1, and delta f 2 is just f 3 minus f 2. So, just by doing these differences we can just get these first order differences, delta f 0, delta f 1 and delta f 2. Again, if we note here that the second order derivative, second order difference operator is nothing but the, when we apply this operator here, so that means delta f I plus 1 minus delta f I. So, again we have obtained already here the first order differences, that means these are the deltas here, and again if we do the same exercise. So, we compute here delta f 1 minus this delta f 0, and as per the definition here this is nothing but delta 2 f 0. And similarly, here when we compute this delta f 2 minus delta f 1, this difference we will get delta 2 f 1. So, by repeating the same exercise we will get the second order differences, that means delta 2 f 0 and delta 2 f 1. And similarly, when we go for the third order, again we have to use the same thing. So, we have already the values for these delta 2s, and then we can go for the differences again, and we can get this delta 3 f 3, that means this is delta 2 f 1 minus this delta 2 f 0. So, this difference here will give this delta 3 f 0. So, it is very easy to construct this difference table. Given the values here of this f, we will go with the differences here, and then we will get these first order differences. Again we will go with the differences, we will go second order, and again the differences we will get the third order differences, and so on. There are more data points, so we can go with fourth order, fifth order, etc. So, given these 4 data points, we are going up to the third order differences. Similarly, the backward difference table we can construct, and here also the idea is same. So, we will construct exactly in the same way. So, there is no difference here in the calculations. The same table can be used for forward difference operators and the backward difference operator, only as per the definition which we will see. Backward delta, for instance, now here I am talking about delta f 1. So, what will be delta f 1? F 1 minus f 0. That means, the value which we will get here by subtracting this f 0 from f 1, we will get now backward delta f 1, though here it was forward delta f 0. So, that is the only difference. So, constructing table will be the same, but now we will get, instead of this as delta f 0, in the backward notation we will say it is a backward f 1, this is backward delta f 2, backward delta f 3. So, that is the only difference we have, and again we go further with these differences, and we will get the second order delta 2 this f 2, delta 2 this f 3, and then again we go with the difference. So, we will get the third order. So, usually we will observe in this Newton's forward and backward difference formula. In the forward difference formula, we will be using these values here of the forward difference from the forward difference table. These values will be used, whereas for the backward difference formula, these values will be used, whereas here these values will be used. So, we will form a same table, and we can use either the forward difference formula, which we will derive now, or backward difference formula. Accordingly, we have to select the values from the table, but the table, the construction of the table will be actually the same. So, or the same table can be used for forward difference operators or for the backward difference operators. So, the difference table, just a very simple numerical example again. So, for instance 0, 1, 2 x values are given, and then we have the y values. So, 1 to minus 1, and we want to construct the table which is valid for forward or the backward operators. So, we will go for the difference 2 minus 1. So, this is 1, that is 2 minus 1, here this is 1 minus 2. So, this is minus 1, and then again we will go with the difference. So, here this minus 1 and minus 1. So, minus 2 will be coming as the second order operators. So, when we want to have the forward difference operator, that means the delta f 0, that 1 will be the value, and delta 2 f 0, that will be the value. When we are talking about the backward operator, so backward f 2 will be this one, and backward the second order backward operator on f 2, that will be this minus 2. So, we can use these values for the backward and those upper values for the forward operators. Coming to the Newton's forward difference formula, we have now we will discuss first the linear interpolation case, a very simple one. When two data points are given, we can connect it through a point. Then we will go with the quadratic one, and then we can generalize for n plus 1 or n given data points. So, this is the simplest way to connect two data points with a straight line. So, given data, suppose we have this x naught, we have f x naught and x 1, and we have f x 1. So, suppose we have the function here, the f, the actual function is given, and then there are two data points given to us, and we want to construct a linear interpolation, a linear polynomial or polynomial of degree 1, which passes through these 2 points, that means this line here. So, we can consider the equation of the line, which we have written in this form in little bit fancy way, that b naught, a constant b 1 x and minus x minus x 0. It is a linear function. It is like we can write like a 0 plus this a 1 x. So, this is equivalent to this only, but we have just written in a slightly different form, because one can notice that this is b 0, then we have b 1 x, and then we have b 1 x naught. So, this b 1 x naught and this b 1 is a constant again. So, we have b 1 x and plus some other constant. So, that is the standard equation of the line. So, this is a standard equation only, but we have just written in this way because of we will see in a minute that the evaluation of these coefficients will be much easier if we write this equation in this format. So, for at this point x is equal to x naught, we have both the values, that this polynomial should match with the function values. That means, this p 1 at x 0 should be equal to f x 0, and when we are putting here this x equal to x 0, this term will get cancelled, and we are getting directly b naught, and this is the point we have taken this equation in this particular format. So, we are getting b naught equal to this f x naught, and now at x is equal to x 1 point. So, we will substitute here x is equal to x 1, and this p 1 x 1 will be nothing but the value of the function, that is f x 1. So, here f x 1 is b naught and then b 1 x 1 minus x naught. So, from here we can get the b 1 also easily. So, f x 1 minus this b naught, which was f x 0 and over x 1 minus x 0. So, having these values of b 0, b 1 and this polynomial. So, if we consider the equidistant data point. So, in the forward interpolation formula we will consider, we will assume that data points are equidistant. So, in that case we have some simplification here, that this x 1 minus x naught we can replace by this h, and then here we have f x naught plus h minus f x naught, which in terms of the forward difference operator we are writing now, we are introducing the forward difference operator in our formula. For f x naught plus h minus f x naught we are replacing by this delta f x delta f naught. So, having this now for b 1 and the b naught was just f x naught, our interpolating polynomial of degree 1 can be read as, so f x naught and then x minus x naught delta f naught divided by h. So, this is the forward difference operator which we will get from the table easily. Now, going further to have more general formula. So, let us first derive for the quadratic interpolation. That means, now suppose there are 3 data points, instead of 2 we have 3 data points. We have x naught, we have x 1, we have x 2 and their values f x naught, f x 1 and f x 2 are given. So, now this time to fit this 3 points by a polynomial, we have to consider a second order polynomial, because 3 points are given. That means, we will consider now a second order polynomial again in the same format. That means, a constant term b 1 with the x minus x naught, b 2 the second order term here with x minus x naught and x minus x 1. So, at the point here x is equal to x naught, if we substitute there, what we will get, we have b naught and this p 2 at x naught will be the function value at x naught. So, because this term will go to 0 and this term will also become 0 at x is equal to x naught. So, directly we will get b naught is equal to f x naught. And now, we will go for the second point, that is x 1. So, x is equal to x 1, if we put this term will become 0. So, we have only the first 2 terms there. So, from there we can just compute this b 1. So, b 1 will be f x 1 and this b naught is f x 0 over x minus x 1, and in case of the equidistant data point which we are considering. So, this is nothing but the delta f naught and then this is h. So, b 1 we have got now delta f 0 over h, and now the b 2. So, having this b naught and b 1. So, remember this is the same values what we got also for the first order polynomial. So, now for the point x is equal to x 2. So, we will substitute there, the polynomial value and the function value are same. So, f x 2 is equal to f x 0, we have delta f 0 multiplied by this, we have b 2, we have x 2 minus x 0, we have x 2 minus x 1. So, from here now everything is known other than this b 2. So, we can compute this b 2, and so this is f x naught which is written here, and then we have here delta f naught. First we have written this as f 1 minus f naught, and this is 2 times h. So, basically h will get cancelled, we have 2 times and multiplied to this f 1 minus f naught. So, we have 2 times f x 1 and minus 2 times f x naught, and then from here what we will get h square because of this h and h. Here indeed we have this 2 h and here we have just h. So, we will get 2 h square, and we just for the generalization purpose we have written this factorial 2. So, this is h square with this b 2, and which we can simplify, and we will get the coefficient b 2 in this form, and remember the formula of the second difference operator. So, we can write this delta 2 f naught over factorial 2 h square. So, we got the B2, we got B1, we got B naught. So, we can just put everything together and we have this interpolating polynomial. And the interesting thing is that it is just continuing. So, here it was same for when we derived the first order polynomial, and this term is added now to the formula. So, we got the second order polynomial which passes through the given 3 points. We can continue this derivation for the 4 points, 5 points, or in general we can write down. So, for if the 2 points are given, we have the first order polynomial, if 3 points are given, we have second order polynomial. And the general formula, if there are n plus 1 distinct this nodal points are given, then we can have this nth degree polynomial, where the formula one can see it is just the extension of what we have derived. This is the second order term, and we will continue with this. So, the next term will be x minus x naught, x minus x 1, x minus x 2, and there will be third order derivative there, factorial third order operator, and then factorial 3 and h cube. So, the last term, in this way we can get this nth order operator here on f naught. And then, so what is interesting here, that from the table we can get all these values, delta f naught, delta 2 f naught, delta n f naught, and the rest is already there in the formula. We can get a polynomial easily. There is another form also in the literature one can find, that if we substitute this x minus x naught by h as u, another just a change of variables kind of thing. So, x minus x naught over h, if we substitute as u, then this formula can be written as in this form p n, and this x is nothing but from here we can get h u plus x naught. So, x naught plus h u, and then we have this f naught, which is a short notation for f x naught, and then here x minus x naught is h u. So, h h gets cancelled. So, we have basically only u and the operator. So, what we do see here, that in this case now it is little bit simplified. We can use this from the difference table, and the rest is just u minus 1, the h is disappeared now from everywhere. And so, this is another way of rewriting this forward difference formula. So, the same derivation, there is just a quick view to derive this in a different way. So, f x we can write down as x naught plus x minus x naught over h. So, you just see that h h gets cancelled and x naught get cancelled, and we have still f x there. So, having this now, and we know the notation only, that x minus x naught over h we are taking as u. So, taking this, we have this one x naught plus u h. By this shift operator, we can say it is a e operator, this u times, so e power u and f x naught, because this was exactly what we have learned there, that this value will be x naught plus this u times h. So, this is a quick derivation sort of, which will lead to the formula which we have just derived, and that relation also we have seen that e we can write 1 plus delta, again this power, this u will come f x naught, and then we can expand this 1 plus delta power u, it is a kind of binomial expansion. So, we have this expansion here 1 plus this u times delta, and then the u minus 1 factorial 2, u minus 1 u minus 2 over factorial 3, and so on. So, having that now we got exactly this formula, but there are infinitely many terms. So, we have to truncate this. So, neglecting the differences the n plus 1 and higher order differences, we get the above formula. So, if we neglect all these differences which are coming which are bigger than this n plus 1, we can get the desired formula which we have just seen above, and replacing again u by this relation, we can convert into the form x and h. So, there is a Newton's backward difference formula. Having this Newton's forward difference formula, this is much easier now to talk about this. So, again we will use this quick approach to derive this formula. So, we have f x, and now we will start with this f x n minus plus this f x minus n over h. So, again h gets cancelled, this x n gets cancelled, we have still f x, and that can be written as f x n plus h u. So, this again can be written as e power u f x n, and which this relation we will use, that backward operator is 1 minus e, or this e minus 1 is nothing but 1 minus this backward operator, or e is nothing but 1 minus backward operator power minus 1. So, this relation we can use there, and so we have 1 minus this backward operator power this minus u, and then f x n. So, again this expansion of this will lead to the u plus 1 factorial 2 u plus 1 and so on factorial n, and then we have these operators there. So, now we have the backward operators, and again truncating the or neglecting the differences n plus 1 and the higher order, we will get exactly the formula which we are looking for. So, this is the backward difference formula which can be used now in terms of u, and if we want to get back to x, so we can just use this relation that this is equal to u, and we can rewrite everything in terms of this x and h. So, this is the backward difference, Newton's difference formula. These are the references we have used for preparing the lecture. So, just to conclude, in this lecture we have discussed the Newton's forward difference formula, which uses these forward differences delta f naught, delta 2 f naught, delta n f naught, and we have also discussed the Newton's backward difference formula, the difference mainly that instead of this x naught we go from the backward direction. So, we take the f at x n and then x minus x n, and instead of the forward we have the backward operator on f n divided by h, and then here x minus x n, x minus x n minus 1. So, we go from the backward direction, having remember this one formula, other one can be written because it is taking from the forward direction, this is taking from the backward direction, and similarly the other higher order terms can be interpreted. So, that is all for this lecture, and I thank you for your attention.